Hi everyone, I'm Kareem, a PhD candidate at the University of Munich. Today I'm excited to present my paper, Pairwise Difference Learning for Classification, recently accepted at the Discovery Science Conference 2024. In this presentation, we will introduce Pairwise Difference Learning, or PDL, a new machine learning algorithm compatible with Scikit-Learn. Through this presentation, we'll explore how it operates in both regression and classification tasks, with potential for easy extension to other tasks as well. Our experiments on standard benchmarks demonstrate that PDL outperforms leading algorithms like random forest. Plus, it's straightforward to use, thanks to the publicly available Python library. More on that in next slides. PDL is a machine learning meta-algorithm that learns the difference between pairs of inputs rather than their absolute values, leading to better performance. Regression versions of PDL were independently developed by Tynes et al. And Wetzel et al. Our contribution is a model-agnostic implementation of the classification version of PDL. In a separate paper, we also introduce optimization methods to weight PDL effectively. To start, let's go over how the regression version works. Given a training set with n points, we can train a model, say G, to predict the number of edges for each point. For instance, GI could be a random forest regressor. PDL regressor takes on a dual task by pairing the training points. This pairing creates combinations like star-square, star-star, circle-square, and so forth. For each pair, we calculate a new target that represents the difference in edges. For example, a pair of star and square points would have a target difference of 10 minus 4 equals 6 edges. If the pair contains identical points, the target difference would naturally be 0. Any regressor, such as gamma, could be trained on this task, possibly the same random forest regressor we used before. To predict the target for a test point, we pair it with each of the n training points. With these n pairs, we apply gamma to estimate the difference in edges for each pair. Since we already know the initial values of the training points, we simply add this difference. For instance, if the first pair is a training point star with a known target of 10 and a difference of -4.3 with the test point, the prediction is 10 minus 4.3 equal 5.7 edges for the test point. We obtain n predictions and take the average to get the final result. Comparing the test point with all training points, we ultimately predict it would have around 6 edges. The PDL regressor and its variants have shown impressive performance across diverse applications, including regression with image inputs, predicting chemical properties, modeling quantum mechanical reactions, and ranking drug activities. PDL is also highly scalable, as demonstrated by its success with large datasets, like the Phi-DFTB dataset with 11,000 features and 12,000 data points, highlighting PDL's capacity for large-scale, data-intensive challenges. Our contribution introduces a model-agnostic classification version of PDL. In this version, we don't use subtraction to learn differences. Instead, we learn similarity based on target equality. If a pair of points share the same target, the new target is set to 1. If they belong to different classes, the new target is 0. While the original classification task may involve multiple labels, this new task is binary. In the prediction phase, we pair the query point xq with each training point xi. The model G of xq(xi) predicts the similarity of the pair, that is, the probability that xq belongs to class yi. For the remaining probabilities, we update the prior using the given formula. Finally, we average the predictions from all pairs. We can turn the previous example into a 3-class classification problem. To use the PDL classifier, we pair the training points and label them as either similar, 1, or different, 0. While G was solving a multi-class classification problem, gamma handles this as a binary task. To predict the class of a test point, we pair it with each training point and predict the similarity. The predicted probability is assigned to the class of the training point, and we update the remaining probabilities by adjusting the prior. Finally, by averaging over all rows, we obtain a single probability for each class. In this case, the test point is most likely to belong to Class 3. Pairwise Difference Learning is model agnostic, meaning it's compatible with any baseline ML model. Let's take the example of the Moon's dataset. While a 3 nearest neighbors algorithm typically predicts discrete probabilities, the PDL classifier applied on top of KNN can produce a smoother boundary between the two moons. The same applies to other baseline models. PDL learns more fine-grained patterns. We evaluated the PDL classifier on a large set of tabular datasets from OpenML, covering a variety of data points, features, classes, and levels of class imbalance. We used 5 repetitions of 5-fold cross-validation. To ensure accuracy, hyperparameters were tuned with nested cross-validation. Our comparison includes 7 state-of-the-art ML models, along with their equivalents using the PDL classifier. First important results: the pairwise models achieved the highest average F1 score across the benchmark datasets. Pairwise PDL, on top of extra trees, emerged as the best-performing model. However, for faster training, even a pairwise model using a simple decision tree is sufficient to outperform all standard Scikit-Learn models. Now, let's examine the results on each dataset individually. We compare the performance of each baseline model with its pairwise enhanced version. In most datasets, the pairwise model significantly outperforms the baseline, making it the preferred choice for higher performance. A question arises: why does data pairing lead to improved performance in 90% of the datasets? Our first assumption is that learning the difference between pairs is simply easier. For instance, consider the Boston dataset, where the goal is to predict house prices. Given a pair of similar houses, it becomes straightforward to predict the difference in price. Second hypothesis: averaging the predicted differences creates an ensemble effect. Imagine asking several people about the height of the Eiffel Tower. While each individual may provide an inaccurate estimate, their average is likely to be the closest to the actual height. Similarly, PDL classifiers predict multiple differences, and averaging these predictions brings us closer to the correct answer. Third hypothesis: simplifying the multi-class task problem into the binary case. Distinguishing between multiple classes can be complex, whereas solving a similar or different task is often easier. Let's examine these effects using 4 datasets from OpenML. For each dataset, we measure the baseline loss in blue, the PDL loss with a cross, and the gamma loss, which represents the PDL loss using only a single pair for prediction. In dataset A, the gamma loss already outperforms the baseline loss, showing that the ensembling effect wasn't even necessary for improvement. In dataset B, learning the difference alone isn't sufficient. However, the ensembling effect reduces the loss by 65%, allowing PDL to outperform the baseline. In dataset C, PDL doesn't outperform the baseline. However, based on the observed trend, adding more anchor pairs during prediction could potentially reduce the loss further. Lastly, in dataset D, neither the current PDL loss nor the theoretical limit with additional anchor data is enough to surpass the baseline. Approximately 60% of the datasets fall into case A, around 30% into case B, and cases C and D combined represent about 10% of the studied datasets.
Pairwise difference learning is highly efficient with small datasets and is an ideal model for the automotive field, especially given the current advancements in the industry. Let's take the vehicle safety dataset as an example. The goal is to predict whether a specific combination of restraint systems provides the highest safety standards for occupants. One challenge with this relatively small dataset is that acquiring additional data points can be quite costly. Furthermore, the shift towards electric vehicles has resulted in a data shift, making training on older car models less relevant. For these reasons, pairwise difference learning is the perfect choice for this task, and it has indeed demonstrated the best performance. In practical terms, PDL is easy to use thanks to its publicly available Python library. First, install it with pip install PDLL, import the classification or regression version, load your data, select a baseline model, random forest for example, is a good choice if your data has missing values. Wrap your baseline model with PDL. Finally, fit the model. The rest of your code can remain unchanged, as our solution is fully compatible with Scikit-Learn. If you're wondering whether Pairwise Difference Learning is a good fit for your problem, this checklist can help you decide. If you want to improve performance on a classification or regression problem with fewer than 10,000 training points, and the data is tabular, then PDL is an excellent choice. You can start directly with the library. With a bit of coding, PDL can also be extended for semi-supervised learning or adapted to handle text, graphs, or images. Keep in mind the training set size. For datasets beyond 10,000 points, a supercomputer or HPC may be required. Overall, you can expect around a 10% improvement in performance. Thank you for your attention. To access the GitHub repository, scan the QR code on the screen. For any questions or further discussion, feel free to reach out via email. Thanks.